There are several patterns of logarithmic equations, and I will try to address each of them in this video. In this first problem, notice I have log base 5 of argument equals log base 5 of argument. Since basically I have log equals log, I can set the arguments equal to each other. C squared minus c is equal to 20. Basically, you might say that I've taken the anti-log of each side. Now that I have a quadratic equation, I can set it equal to 0, and then factor and solve this. C minus 5 times c plus 4 is equal to 0, and it appears that c is either 5 or negative 4. Now we do need to check these solutions because we're not allowed to have the log of a negative number, and I need to make sure that when each of these are substituted in, we do not get a negative. When we substitute 5 in, we get 25 minus 5, which is 20, and that's log of 20 equals log of 20, so that works. When we substitute in negative 4, we get 16 minus a negative 4, which is also 20. So in this case, both of these answers do check, and that is our solution set. In this next problem, I've got natural log of argument equals natural log of argument. So again, I can anti-log each side and just have y minus 4 equals 2y minus 1. I'm going to subtract y off of each side to now have negative 4 equals y minus 1, and adding 1 to each side, I get y equals negative 3. Now let's check this answer. On the left, I get negative 3 minus 4. That's the natural log of a negative number, and that's not allowed. So in this case, we have no solution. You always need to check that when you substitute the solution you get in, the argument does not become negative. Now we have an entirely different pattern. We have log minus log equals number. And the first thing you want to do is take this subtraction and turn it into the division of 2, or the division inside of a log, giving us log base 3 of 8 over x plus 5 is equal to 2. And unlike the problems above where we had log equals log, I've got log equals number. So we need to convert this from a logarithmic to an exponential function and rewrite this as 3 squared is equal to 8 divided by x plus 5. Now I'm going to write that 3 squared over 1 so that we can then cross multiply. We would have 9 times x plus 5 is equal to 8, and that would become 9x plus 45 is equal to 8. Subtracting 45 on each side will give us 9x is equal to negative 37, and x would equal negative 37 over 9. Now, we don't cancel negative answers for the sake of negative answers. We need to substitute them back into the original problem and see if they will check. This is just a little bit smaller than negative 4. Call it negative 4.1. If we substitute it into the original problem for x, negative 4.1 plus 5 becomes positive, and we've got a positive argument. So yes, negative 37/9 is a valid solution. On this next problem, we have log plus log equals number, and we know that the sum of two logs can be the log of their product. So we will have log base 2 of h minus 1 times h plus 1, which is h squared minus 1, is equal to 3. Again, I've got a logarithmic equation which I'm going to switch into an exponential equation, rewriting this as 2 to the third is equal to h squared minus 1. Well, that is an 8 on the left, so we can subtract 8 on each side to get h squared minus 9, which is a quadratic equation factoring into h plus 3 and h minus 3. So we have two possible solutions, h equals negative 3 or h equals positive 3. But if you substitute that negative 3 into either argument, you will find that you get the log of a negative, so we must cross that solution out and only have h equals 3 as the solution. For this next problem, again we have the sum of two logs, so we're going to write this as log base 3 of their product. K times 2k plus 3 is 2k squared plus 3k, then equal to 2. And again, we're going to convert this from a logarithmic to an exponential equation, rewriting this as 3 squared is equal to 2k squared plus 3k. That is a quadratic equation which we want to set equal to 0, so we would subtract that 3 squared, or 9, on each side, giving us 0 equals 2k squared plus 3k minus 9. That will then factor into 2k minus 3 times k plus 3, and we have two potential solutions. One would be a solution of 3 halves, the other would be a solution of negative 3. However, we know that negative solution will not work because the first logarithm in the original problem has log of k, and k can't be negative. So we will cross off that solution and check the other one. Log of 3 halves is fine. If we substitute 3 halves into the second parentheses, we do not get a negative there, and so it looks like 3 halves is a valid solution. Now we have a totally different pattern. Again, we're going to have an addition problem on the left turning into the product, so we will have log base 4 of 6y minus 7 times 3, which becomes 18y minus 21 inside the log, equals log base 4 of 5. Now we've got log base 4 of something equals log base 4 of 5. If we anti-log each side, getting rid of those logs, we will just have 18y minus 21 is equal to 5, and we can add 21 to each side to get 18y is equal to 26, and divide each side by 18, giving us 26 over 18, which reduces to 13/9. Now let's verify that when we substitute 13/9 in, we do not get a negative in either log, and we're safe here, so 13/9 is going to be our solution.